So hello everyone. So today I'm going to talk about my work in referring expression generation with Rational Speech Act. So first, I would describe the problem and the motivation, why I would want to apply the Rational Speech Act to the problem of referring expression generation. And I will describe the experiment that I have run. So the problem of referring expression has been studied a lot in linguistics settings. However, in computer science, it usually is the context that combines both linguistics and image or computer vision. In this case, in computer science, referring expression generation talks about the task of given an image and a bounded region within an image. The task is to generate an expression that describes the bounded region given the context here, which is the image itself. So here I give some examples taken from a couple of datasets for referring expression. There are RefCOCO, RefCOCO, and RefCOCO Plus. So these datasets are all derived from the image COCO dataset. And in each of these datasets, we have an image and a bounded region. And for example, specific example here, a couple of expressions that describe the bounded regions. So we have, for example, in this particular example, we have the expression woman on right in the white shirt, or woman on right, or just a right woman, which perfectly describe the individual on the box here. And a note is that in these datasets, these expressions are generated by a human being, and the task is to create some machine learning algorithm to generate these kind of expressions. Yeah, so I just basically described that. The task, given an input image, we want and a target object to generate a referring expressions. So in the referring expression generations, currently the most trendy way and the most successful way is using deep learning approaches, namely deep neural nets, and they generate great results. So I will give a brief overview of that and show how my approach is different from this. So using deep learning to the referring expression generation problem, what the common approach in applying deep learning does is divide this task into two subtasks. The first part is to get an image and bounded region representation through an image model, and then using this representation or features from the image and the bounded region to generate a text through a language model. So in this image example right here, the first task of extracting features from the image is handled by a convolutional neural network. And after feeding the image and the boundary region into a convolutional neural net, the output vectors is then used to feed into a trained language model, in this case LSTM, to generate these kind of texts. So this is a very standard approach in deep learning in referring expression generation. Now, to showcase some of the results in deep learning in this task, you can see that MLE and MMI are the standard baseline, and the state-of-the-art approach generates really, really good results. So, for example, the picture on the right here, currently the state-of-the-art models, the re-ranker method can generate something like giraffe closest to us, which is an extremely good description, which is something that probably a human being would say to describe this. Whereas some of the baseline, which is also used deep learning, generates something which is a little bit less relevant, which is giraffe with head down, a tallest giraffe. However, regardless of quality, using deep learning for referring expressions suffer from the same problem as applying deep learning to any problem, is explainability. because of its massive scale, it's really, really hard to explain why a language model generates such word and such word. And this problem becomes worse in recurrent expression generation because usually a language model take input as like the word vector, the vector representation of sentences or words. And these vectorized representations are often derived from like libraries such as like word2vec or some transformation that transform sentences or words into vectors. So in some sense, these vectors at least represent something about the words. However, in REG, the input for the language model are the embedded features of the images and not any sentences or words. So it becomes even more confusing to explain why a model generates such expressions. So there is a room to improvement in terms of explainability there. And before talking about RSA and its application onto the REG, I first talk about Bayesian maxims. And so RSA, or Rational Speech Act, is a linguistic framework that explains human behavior in a conversation. So it has been observed by linguists that in human conversation, we tend to follow these rules called like Bayesian maxims, which are the maxim of quantity, quality, relation, and manner. To explain it simply, so when two logical and rational individual communicate, the speaker would want to say the least amount of words with the highest quality for each of these words, and the words they say should be grammatically and linguistically correct, which kind of makes sense because in a rational world, people would like to say the least amount of things to describe something to the listener. So Rational Speech Act is a framework, is a probabilistic framework that have shown to describe this behavior. And Rational Speech Act is set up by as a two-player cooperative scheme with a speaker and a listener. And specifically, it is a recursive reasoning system that contains a listener, two listeners, a literal listener, a pragmatic listener, and a pragmatic speaker. So this framework is purely based on the Bayesian probability, and it doesn't require any training data. To explain this through an example, I will go through a toy example. In this toy example right here, we have three objects: the blue square, the blue circle, and the green square. So given the world state here, we have three objects such as these. The speaker have to choose one word to describe one object that he has in mind to the listener. Now, here in this very simple toy example, the speaker can choose between one of these four words: square, circle, blue, or green, which describe the properties of all the objects in this tiny world state. So we have a couple agents: the literal listener, the pragmatic speaker, and the pragmatic listener. The literal listener is a listener that take a word and interpret it at face value. By that I mean, for example, if a literal listener hear the word blue, he or she, the listener, would assign 50-50 probability to either the blue square or the blue circle. And if the literal listener hear the word green, he would assign probability 100% to the green square, because only such object have that property. Now, I want you to focus, for example, in this case, to the blue circle, and think about like what should a speaker say in one word to describe this object. Yeah. So as I said before, the literal listener take the word he said and describe it by face value. So if he's heard the word blue, he would say, oh, the speaker probably either 50% talking about the circle or 50% talking about the square. However, a pragmatic speaker, on the other hand, wouldn't do that, wouldn't say a word by face value. It based on Bayesian rules and applying some cost value to some words that he say. In this toy example, all the words cost the same, which is just one. And decide what word he would say depend on the distribution, like the conditional distribution of that property, log of such object, conditioning on the word that he said. And the pragmatic listener is in this case the good listener that listen to this word that the pragmatic speakers say and don't take it on face value. In turn, don't just take the word by face value, but multiply what the speaker said with a prior distribution, and from there he can infer what the speaker would say. So I want to highlight this table right here with the object that we talked about, the blue square. And when the speakers say the word blue, I want to go back to see what a rational listener would think. So, for example, if the speaker has the blue circle in mind, the speaker would have said the word circle because it perfectly describes the object and reduce the entropy basically to zero because it clear all the confusion. So in fact, unlike the literal listener who just take the word by face value, when hearing the word blue, a rational or pragmatic listener should assign a higher value to the blue square because he should have he probably wouldn't refer to the blue circle as blue in this case. As I explained, he would have used the term circle. And based on that, and that is also shown in the calculation of RSA here, that given the word blue square, and the speaker speak the word blue, it is more likely that the speaker is referring to the blue square at 60% than blue circle 40%. Now this is a very toy example. So I want to apply this RSA probabilistic model to the referring expression problem generation task, which is a lot more complicated. And referring expression should also be longer than one word. So I implemented the iterative RSA. The idea behind that is rather quite simple, that instead of just speaking one word at a time, I would iteratively generate one word or one utterance at a time, at each iteration. And then every time the speakers say one word, I will update the prior distribution or the object salience based on what the speaker has said. And then I will cut off after some particular threshold or some level of entropy. So one challenge to apply RSA to referring expression is that in the vanilla example, the input to RSA is actually not the image of the blue square or the image of the blue circle, but actually the word blue, red, blue square, or green or circle, and a prior probability table that say that the probability that the blue square have the attribute blue is 100%, and the probability that the blue square has the attribute green is 0%, and so on. So the input to RSA is actually not an image. in order to apply RSA, I need to have a knowledge extraction step from the image, I need to extract textual information, such as what objects are there in these images and what attributes or what features are there that belongs to these objects. So in order for the knowledge extraction to happen, I apply Detectron, which is a state-of-the-art image processing library from Facebook. And from this library, I could, given any image, I could extract many objects from the images, as well as some attributes related to these objects. So in this case, I take this image right from the source code or the GitHub page of Detectron. And given an image, one can detect these objects, such as like the target, the individual in this is a person, we have a backpack, we have a bicycle, and so on. And to further emphasize on this knowledge extraction step is that when I apply Detectron to RefCOCO images, I also pull out the attributes of it. So, and aggregate all of these data for each of the image into a table data like this. So, for example, given this image and apply and aggregate all the detected objects and attributes, I get this kind of example. So for this image over here, Detectron could detect some objects like these. So we have a dress, a man, a group of people, a flag, a building, and so on. And each of these actually have some attributes associated with it, such as like whether the attribute thin is associated with some of these objects, or is it a yoke or decorative? There are like many objective attributes associated with these objects that is predefined by Detectron. So from this information, I then feed this information to the RSA and use the output to evaluate that against other end-to-end approaches. So here are some of the results that I have run against the state-of-the-art approaches. And before explaining this table, I have to again stress that the strength of RSA is that it doesn't require any sort of training data, but just based on these like knowledge information from the images and the attributes, it can generate the expressions. So in order for fair comparison, I both like take the output of RSA and compare that against the state-of-the-art methods using standard NLP metrics. And I also set up a low resource training process where I only use part of the training data to train a state-of-the-art model. So when I take my model, RSA, comparing to all the state-of-the-art deep learning approaches, unsurprisingly, many of the standard NLP metrics, such as blur, rouge, or meteor score, iterative RSA falls short when compared to the deep learning approaches. However, when I apply the low resource training scheme, iterative RSA actually performs slightly better when SLR is strictly listener reinforcer, which is one of the state-of-the-art deep learning approach for REG. So iterative RSA outperform when SLR is training with only 10% of the data, and greatly outperform if the SLR model only have 1% or 0.1% of the training data. Also, the other columns in this table down here is actually a survey that I implemented because the NLP metric, as many people have been criticized blur, is that it doesn't capture many of the it doesn't fully capture the meaning of a sentence. So I created a survey and run a survey on human participants to evaluate the generated expressions across different methods like this. So in this survey, I have a couple of options for human participant to choose from. Either if the human participant can click on the correct bounding box, then it is recorded as a true response. If the human participant click on the wrong box, then it's a false. Or if not, if the human participant decided that the information is not good enough to determine, then he can choose among these three options that either the generated expression is underinformative, or there's no match in the image, or there is a match from the referring expression and the image, but it's not highlighted. Yeah, and the adjusted accuracy here is when I only count accuracy between the true and the false, means that the human participant determined that there is enough information to click on a box. So in that case, also iterative RSA perform better when compared to a deep learning approach that only train on a small amount of data. So lastly, I want to emphasize the explainability part by showing some of the results from the survey that I implemented. So the survey tool that I implemented. So here, when applying RSA, we can, beyond generating an expression, we can also analyze why an expression is good or not good, and in what way is it not good. So here, for example, in this image, the target here is the pizza on the left, box number 2. Number 2 is kind of small. And with RSA, I could generate the expression cooking pizza. However, the goal label or the label generated by human being is pizza on the left. So in this case, a human participant has chosen that this is underinformative, and this is a great information because it shows that, okay, RSA, in this case, it falls short because here it generates the term cooking pizza. The order of generation is first it generates the term pizza because it's the most descriptive, the best description as a first descriptor. And then in the second iteration, among all the properties of this pizza, it chooses the word cooking, which is not good enough to discriminate this from the pizza on the right. The next example is when the object is not highlighted. So in this case, the RSA generated laying down man. But in this case, this is not the fault of RSA because Detectron cannot detect all of the human being in this image. And the true target here is actually box number 2 again, but Detectron 2 cannot detect this object. So it's not possible for RSA to generate an expression that is not highlighted. So the last example is an example where RSA works really well, and the human survey also show why it works well. So in this case, the human participant correctly identified the target, and the generated expression from RSA is the right train. And by using RSA, I can probably say that the first descriptor that RSA generated is train, because it's the best descriptor that have many of the confusion, and it reduced the search space into only 2 objects, the train number 4 and the train number 5 here. And among them, those 2, in the next iteration, it generated the term the right, which is the perfect descriptor for this object. So to wrap up my presentation, from this research, I have found that RSA provides a great explainability such as why a generative agent generates such word and utterance, and if the expression is not good, then where does it fall short, and how can we improve it? And we also found that RSA, because of its nature that it takes input as like texts, it is highly dependent on the feature extraction algorithm. In this case, is the detectron algorithm. And the last takeaway is it also outperforms compared to low resource scheme in the deep learning model as a fair comparison, because RSA doesn't use training data. So that wraps up my presentation. Yeah, and I take any question for my work. Thank you.
Thank you very much. That was very informative. Anyone have a question for the researcher?
Yeah, I see one question from Dina.
No, thank you, Professor. I said thank you.
Okay. Yeah, I can't see the chat room, so is there any question from the chat room?
Yeah, no questions. Maybe out of my own curiosity, obviously when you're dealing with images, it's quite resource intensive. What are some of the libraries, or what are some of the infrastructure that you use to run the simulation, so to speak?
Oh yeah, sure. So in terms of the knowledge extraction step, it's actually not very hard to run, because as I said, I mean, in order to get this like textual information, to get this on my own would be extremely hard. But institutions such as like Facebook AI Research have already developed this tool. It's called Detectron, and the tool is fully available on GitHub and installed through like pip. So yeah, I think it also helps if you have a GPU to run this like image extraction tool. Yeah.